At this point, you should be good at problems like these. We've got 5 people. We're going to select a president, a vice president, and a secretary from that group. So we know that there are P53, which I've written here as 5 factorial over 5 minus 3 factorial, which works out to be 5 times 4 times 3, or 60 ways to do this. Now, when we do this, the order of the peoples matters. So, for instance, if we picked out A, B, and C out of our group to be president, vice president, and secretary, that's a different group from B, C, and A being president, vice president, and secretary in that order. Sometimes, though, we just want to pick out a group of 3, and it doesn't matter what their order is. We call that, instead of a permutation of 3 taken from 5, a combination of 3 taken from 5. There are 3 factorial ways to arrange those 3 people. 3 times 2 times 1 is 6 ways. So if we've used permutations to answer the question, in how many ways can we pick 3 where order doesn't matter, we've counted 6 times too many, and we've got to divide that out. So here's our problem. We've got 5 people. We're picking 3 to serve on a committee. It doesn't matter the order they're in. They're just on the committee. When we use permutations, that's 60. That assumes the positions on the committee are different. In this case, they're not. We have to divide by the 3 factorial, or 6 arrangements, to find the right answer. So the number of committees is our old computation, which is 5 factorial over 5 minus 3 factorial, and we need to divide in the denominator by another 3 factorial to divide out all the arrangements. So what we have is 60 over 6 equals 10 possible committees. The rule is that the combination of R items, combinations is the word for a group where order doesn't matter, of R items taken from a group of size n is CNR equals n factorial over n minus r factorial times r factorial. You should notice that the section I'm highlighting here is just the old permutation formula. And what makes it a combination formula now is that we are dividing, putting in the denominator, another r factorial. We're dividing out all those ways to arrange those people. Okay, so here's an example. Suppose we've got 10 players on a team. We're going to choose 5 for starting lineup. We're going to assume it doesn't matter that all of our players can play any position, so it doesn't matter from that standpoint. How many starting lineups can we choose? Well, the answer is the number of combinations of 5 taken from a group of 10. By our formula, that's 10 factorial over 10 minus 5 factorial times 5 factorial, which works out to be 126. So there's 126 starting lineups of 5 players taken from a group of 10. The problems in section 2.3 are similar to this example. Almost all of them use combinations, and your key that it's going to be a combination is that the ordering of the people in a particular group isn't important, like the number of people on this starting lineup or the people in the committee. If you see something like it's a group in a play, and we're doing a cast, and people have certain roles, or president, vice president, secretary, those are ones where you'd be using permutation. So good luck on your homework today. Check Moodle for it. Have fun.